Hey, hello there, and welcome back for more Advent of Code. So today is December 22nd, and it's not so late at night for once. And look at that, it's really nice having already like 3 things flowing down. And I guess we'll have a 4th one soon, and I don't know if a 5th one. Yeah, it should, finally it should start snowing at some point. But yeah, it's not so late at night for once. So today we have the opportunity of maybe catching up to day 22. Right now I am on day 21. And yesterday we did day 20, which was, it was quite a challenge. I don't know if I will upload a video of that because it's basically me spending like 1 hour just parsing inputs and trying to wire things correctly, or even more than 1 hour doing that, and then like 2 hours and something just hacking and stumbling on things until I finally get an answer. So that was nice, but it was a struggle. So hopefully today's puzzle won't be of this sort, because the problem with yesterday's puzzle, I think it was one of those puzzles that requires you to do something like understand the input specifically, like what the input is doing and like the edge cases that input has, and implementing something that is very ad hoc for that input in particular, which I think I like doing every now and then, but I don't like those to be like the norm, and usually they aren't. Like it's only been like one puzzle of that sort in this whole Advent of Code. So I don't expect today, day 21 to be the same, but let's see. 21, step counter. And speaking of counters, actually, I forgot to put my stopwatch, so let's do that. You managed to catch the airship right as it's dropping someone else off on their all-expense-paid trip to Desert Island. Yeah, so the airship was from day 7. I think it was the way that we got to Desert Island. It even helpfully drops you off near the gardener and his massive farm. So the gardener is reference to day 5, and that's nice. It's referencing all the previous puzzles. You got the sun flowing again. Great work. Now we just need to wait until we have enough sun to filter the water for Snow Island, and we'll have snow again in no time. While you wait, one of the elves that works with the gardener heard how good you are at solving puzzles. Well, indeed. And would like your help. He needs to get his steps in for the day. Wait a moment. The steps here is a link to pedometer, I don't know how this is pronounced, but yes, a step counter. Okay, that's what we are doing, yeah. In for the day, and so he'd like to know which garden plots he can reach with exactly his remaining 64 steps. Okay. By the way, I was wondering, like here the gardener talks about you got the sun flowing again, great work, and I'm wondering, like, does this text appear if you didn't solve the previous day and jump into this one? I don't know if Advent of Code has like dynamic text for that sort of things, but it would be nice, like a nice nugget there. So okay, we have a garden. Oh, it's a grid puzzle. Nice. So which garden plots he can reach with exactly his remaining 64 steps? 64. Interesting. Power of 2. He gives you an up-to-date map, your puzzle input, of his starting position, S, garden plots, dots, and rocks. Hash. So once again, a grid puzzle with dots and hashes. What could go wrong? The elf starts at the starting position, so here I guess, which also counts as a garden plot. then he can take one step north, south, east, or west, but only onto tiles that are garden plots. This would allow him to reach any of the tiles marked O. Okay, so yeah, simple like wall detection on these, what are these? Rocks, okay. Then he takes a second step, since at this point he could be at either tile marked O. His second step would allow him to reach any garden plot in one step north, south, east, or west of any tile that he would have reached after the first step. Okay. After 2 steps, he could be at any of the tiles marked O above, including the starting position, either by going north and south or by going west then east. Okay, so he can, was this the starting position? I think so, right? Yeah. So he can go left and then right and end up at the start again. A single third step leads to even more possibilities. Okay. He will continue like this until his steps for the day have been exhausted. After a total of 6 steps, he could reach any of the garden plots marked O. So this is after 6 steps. It's interesting, like the parity thing here. In this example, if the elf goal was to get exactly 6 more steps today, he could use them to reach any of 16 garden plots. However, the elf actually needs to get 64 steps today, and the map he's handed you is much larger than the example map. Starting from the garden plot marked S on your map, how many garden plots could the elf reach in exactly 64 steps? Okay, so this doesn't sound too hard, at least part 1. So the input is a giant map, and here's the starting position, and it has some interesting shapes, this thing. Like there seems to be like a I see it. There seems to be like a giant, how do you say, rhombus or diamond shape. You can see it here, like this way and this way there are 2 lines, and if I scroll down there's 2 lines like this, and that's interesting because when you move in this like 4 direction possibilities, you know, like a circle of a given length around you, like say 64 length, for example, is actually a diamond, a diamond shape, because this is like not Euclidean distances. This is like taxi cab distances, so, or Manhattan distances, I think they're also called. So I bet you that these lines are roughly at 64 long distance from the start. And these things, like there are some walls that prevent us, like they should prevent us from being like a perfect diamond, I guess. Because that will be a simple solution, like say we start here and we just draw a diamond, or like what are all the points that are 64 length from here, but just doing the length as a difference in latitude and longitude, I guess, or in x and in y and x positions. But that won't work because we wouldn't be taking the walls into consideration. So this is actually kind of like a pathfinding problem, but it doesn't sound so hard. Like, I don't know if it's going to need an actual, you know, pathfinding solution or a fully fledged pathfinding algorithm. But I don't know. Let's do our usual thing of copying the. No, I'm renaming the template. I didn't want to do that. I wanted to copy it and now rename. Okay, 21, I never automated this part. Step counter. That is what we are doing. And this is 21. So an interesting thing about this puzzle, what did I do there? I'm not sure. Do I have changes? Okay, yeah, it's just the files that I just added. Okay, let's copy the inputs and then talk about this thing that I was thinking of. Copy, paste the sample input. The sample is a bit annoying in that we are given a sample and an answer for 6 steps on this sample instead of the actual 64. That means that we need to like special case the sample and the real input somehow. But it's okay. That's actually, by the way, something that I ended up doing for yesterday's puzzle. So if you have watched the video by any chance, I left this thing like uncommitted. It was just a mess at the point that I got the answer to part 2 because my brain was toasted at that point. But after that, I just did a ad hoc solution asking if, special casing if it is the real input or the sample, and I detect that by detecting this connection to the Rx module that has to do with something about the yesterday's puzzle. So if it is the real input, then I do something special in 2 different places. So only for the real input I'm printing part 2. Like part 1 part 1 didn't make sense for the sample inputs that we got. So I have no problem of special casing this kind of thing. Although maybe the structure of the structure that I chosen for the project of having like different standalone executables and then input files as separate things might be something to consider, to reconsider. But yeah, anyway, like I could also have this, since these are standalone executables, I could also make them do like whatever I want. I could make, for example, the problem on day 20, take a parameter, like a command line argument, asking run part 2 or not. Or I could make today's program like take a parameter that specifies how many steps to count. So that's also possible, and then on my test or whatever I will pass different parameters depending on whether it is the sample input or not. But either way, it's fine. So how should we do this? Okay, one thing that I was thinking about is that what we are asked to do is which garden plot this elf can reach exactly in his remaining 64 steps. So it's not all the garden plots that he can travel to, like in 64 steps or less, is exactly in 64 steps, and that creates an interesting pattern. You can see after, this is 3 possibilities. After 6 steps, you can see all the O's where he can reach. But of course, he has also traveled to these plots in between the O's, but he cannot reach that in a step, in an even steps. These things sort of have parity, so they will alternate. This plot will be reachable on odd steps, and this will be reachable in even steps, and so on. It's like they have their own parity, and that is quite easy to check. Actually, it's like a checkerboard pattern, and you can know if like a single tile is like even or odd by adding up its x and y coordinates and seeing if that's that number of adding x and y is even or odd. So one possible solution would be to do like a simple fluid filling thing, and doing 64 steps of fluid filling, or like you could do that by starting at the starting position, putting a 64 there, like saying, okay, I have 64 remaining steps, and sort of fluid fill in every direction, avoiding walls. And every time you fluid fill, you mark the adjacent tiles that you can visit with one less than the number that you are coming from. So 63 and then 62 and so on until you cover everything that you can reach, until you reach 0 basically, and then you stop. Like that's the outer walls of your fluid filling, and then you would have marked every possible tile that you can reach within 64 steps, and then it would be a matter of counting them but filtering out the even or odd. And I think it would be, well, we have to see the parity of the starting position, and then check the tiles that have the same parity as that. And that should be it for part 1. Like, it's not so difficult to implement something like that. So should we go for that? I'm wondering also if our Dijkstra, like our pathfinding package that we used for, I don't know which day it was, if we search for Dijkstra, or Dijkstra, day 17, we used this thing. So is there something like Dijkstra but visiting like more than one ending position, or every ending position? Like, can I ask Dijkstra to say, hey, give me all the nodes that you reach in 64? Because it's not so difficult to implement that. And look at that, yes, there are a couple: Dijkstra all, Dijkstra partial, and Dijkstra reach. What do these things do? Determine all reachable nodes from a starting point, as well as the minimum cost to reach them and possible optimal parent nodes using yes. Okay, this could also be used because it gives you back a hash map of nodes to some node with a cost. I guess they would point to the parents or something. The result is a map where every reachable node, not including start, is associated with an optimal parent node and a cost from the start node. Okay, and you can build the path. Okay, that's good. We could actually do this with this. What are the others? Dijkstra partial. It also takes a stop function, because the Dijkstra all, if you notice, it didn't take a stop function or a goal. But what does the partial do? Determines some reachable nodes, so it also returns the thing kind of like the previous one, reachable nodes from a starting point, as well as the minimum cost to reach them and a possible optimal parent node using blah. Okay, but what does it do differently? It's a function which is called every time a node is examined, including start. A true return value will stop the algorithm. Okay, result is a map where every node. Well, we could use this too, I think. Yeah. This stop function, what does it take? Fs is, it takes a node. Yeah, we could use this and say, hey, stop once you visit any node that, or any tile that is more than 64 tiles away from the starting position, but like measuring in simple distance. And so you stop that, And then you have all of your nodes that are at less than that, basically. And yeah, it will include, I think, some outliers, so you have to filter this with the cost, but you are returned the cost also. So this seems promising. And what is the other one? Like I'm learning about this library now. Dijkstra reach. Ooh, it returns. It doesn't have a stop function, but it returns a Dijkstra reachable. Visit all nodes that are reachable from a start node. The node will be visited in order of cost. With the closest nodes first. And and the successors function also receives the best cost to that node and returns an iterator. Okay. It's interesting that the successors here works differently, but if this thing returns, what is this? Like if it returns an iterator and it's a lazy iterator, maybe this is the best thing to use. Dijkstra reachable. So is this thing an iterator? Yes, it is an iterator. Interesting. I'm tempted to try this one out. I'm really curious of why it needs the successors to also receive the successor function to also receive the cost up to that, because all the other Dijkstra things could have done that, I think. But this one, yeah, we can stop the iteration here with this one. Yeah. This one seems like the best one so far, I think. Yeah, why not? And like Dijkstra all, for instance, the successors, it doesn't take a cost. So let's try to using this one, Dijkstra reach. So yeah, what things you can reach with these? Okay, so first we're going to need to parse things, as we usually do. We need to parse things and also find the starting position. The starting position will also should also be considered a reachable point after 64. That's also probably an off by one error that we could make. Okay, so how do we have our grid? Let's say I'm tempted to just have the grid as a starting thing. Let's say just the most simple one, just a vector of characters, and do input lines as usual. Let's close this thing. We're gonna map each line, and then we're gonna collect each thing. And each line we're going to map to, well, the characters on that line and collect those things. Okay, that should be good. And yeah, something that I wondered is like, okay, this works, but is it better, like, is it shorter to use collect vec from iter tools and collect vec again here and like not declare this thing? I think that is possible, right? Yeah, this also works. And it's like, it is more succinct, I think. It's pretty nice. I wonder if I should use this more often, because iter tools has been really amazing as a library, to be honest. Some things are like just simple utilities like this, but some other things are super useful. So okay, this is the grid. Let's also have the starting position. So how are we going to do that? We can say let, I don't know, start position. It's gonna be the grid, and we need to we need to iterate this every row. So we're going to find the S on the row. So this is basically like a find map, I think. We're gonna have the row, and we want to find in this row a character. Let's call it style, where the style is an S, capital S. Right, so this is, yeah, an option of character, sure. And we need this thing to exist, so this should be okay, or it's an error. Starting position not found. And we propagate this error up. And your problem here is what? Cannot compare. What? Isn't tile here? Is this a double reference? Because find? Yeah, it is a double reference. Sure. Okay. And starting position now is a reference to char with which we can dereference and have a simple thing. Oh, actually, no, this is not the starting position. This is just an S. Why would I want this? So we need to have X and Y. And you know what? Like, that is easier, I think, to just do 2 for loops, I think. So how do we want to deal with this, like, in terms of having signed or unsigned integers? I don't know, but if I convert this thing to actually like the thing that I need, I would have to do like y and row, and then iterate and enumerate here too, and find the x and tile. And what do we need to do? Basically, it's kind of like a find map what I want here also, right? If this is the case, then it's some x, y, what do I have? And now I don't even know. Yeah, I think that is correct. Else it's none. And all of this is giving me an error, cannot be dereferenced. Don't dereference then. And this thing, what's your problem? Okay. Okay. So that's that's some code just to find something on XY. Like, this is not really nice, I think. We can have just like, if we write this with good old for loops, we can have something that says, like, the equivalent thing would be well, we would need mutation, which is like the bad part of this, but then we can say for, well, same idea, y and row in grid iter enumerate, and for x and tile in row iter enumerate, and if the tile is s, again we will need to reference some things, then assign the starting position to some xy. Okay, and then we can check this. So we can say if some, or we can say let some start position, like we extract this thing, start position, or else we'll return an error. Same idea. Same idea as here. We return this thing. And this is basically the same equivalent code as in this. I think this is quite simpler, I'd say. So let's get rid of the iterator thing. Okay, and we can even probably extract this so we don't say it. So this is find start position. Yeah, and just take the thing as a slice. I'm already bike shedding this this thing. So yeah. And here we can just return the actual thing. Like the code actually became simpler here because we don't need to have a mutable variable, I guess, and we can say, okay, in case we don't get here, we'll return none. And we can actually then even do an extraction here, OKR, and have the same thing. So with the extraction, the code I think even became smaller, which is always nice. We early return. Yeah, look at that. We have the start position after all of that. Okay, and now we can finally do our path finding thing. So, how are we going to do this? Let's just call this Dijkstra reach. We need a starting node, which will be the starting position. Do we need something else for the nodes? I don't think so, right? I don't think so. Now the successors is going to take a position also, xy, and I think a cost. So let's call it cost, and it should return an iterable thing of this the neighbors of xy. So let's say let's do our usual thing of neighbor calculation. How are we going to do? Well, we can say, okay, app will be these, the different directions that we have. Yeah, let's say let directions be up, right, down, and left. Left will be this. Very well. I did it clockwise. I'm never consistent on how to do that, but yeah, that is the Cartesian product that we want. And we're gonna do there's in Twitter and what do we want to do? Map, or we want to like filter map, right? Because we want to filter some of this. Sure. This is basically dx dy direction in x and y coordinates. And we want to filter out the do that bounce checking and wall checking. So we'll do something like what is the character that is at this neighbor position. So actually, let's first declare like neighbor x and neighbor y is going to be our x from here, which is should be a U size, if I'm not mistaken. It's not being able to tell us, but I think it is. So wrapping add signs we can use and add the x, and for y also do the same, wrapping add signs of the y. So this would wrap the x and the y can be signed integers because we need negatives, of course, but this would wrap around, and then we can say grid get for neighbor y. This may be out of bounds, so we only return in that case. We're filtering out things that are out of bounds, and then we do get an x and also filter this out. So what would happen if we did just that and then return an x and y? I'm not doing the walls checking here, but I just want to see like the errors. What? Oh, I meant to use tuples here. Not that it makes a whole lot of difference, but or any discernible difference, to be honest. But let's use little tuples. Why not? Oops. All right. Now this get cannot infer type. What? You know the type of the grids. Dijkstra reach closure is expecting two different. Okay, it takes two arguments. I just assumed that it took a tuple. No, it should take two arguments. Yes. Now the cost is unknown. That's okay. And here, since this is a filter map, we need to return a sum. Okay. So closure to be a closure that returns option use size. We also need to return the cost of moving here. So the cost should always be 1, I think. Right? Unless this has successors. The successors function receives the current node and its best cost up to this node, and return an iterator of successors associated with their move cost. Yeah, their move cost should be 1. It's 1 step to move to this neighbor. And lifetime, blah blah. Yeah, surely if you move this, nope. Give me the error here. Oh, grid, the grids. Yeah, just take a reference to the grids. And is the move semantics here needed? Let's see. Well, it kind of wants it because, yeah, they need to access these x and y that may outlive some things. Sure. Yeah, because these x and y's are parts of. So wait, where do you want the move? Yeah, in the filter map. Yes. Okay. Movie. And now, what is the error? Oof. Lifetime may not live long enough. Return type closure filter map. This value requires. But one must outlive two. So one is this, must outlive this. But you are moving things into... Oh, is it that if I dereference this? Yeah. Sometimes these errors are a bit difficult to understand, but I think I understood what happened there, because I was taking these things as references, and this closure, well, it was copying the references itself because we are using move here, but the problem was, so it needs to use x and y, but since it was taking them as references, the x and y had to outlive this thing, and that was not the case. So if I now that I have references there, do I still need the move? Well, I think so, because it's probably borrowing. Well, yes. Let's use the move. Okay. So these are the things that we need to reach. Now, this returns an iterator. Let's then say, let's reachable tiles. It's gonna be this thing. And we still need to implement a couple of things here. So in checking the walls. So if the character, or let's call this thing tile, if the tile in this neighbor is a wall, then we should return none. So we should filter this out. What? Oh, I'm assigning here. Sorry. And one other check is that if the cost is greater than 64, I don't want to consider this, or no, actually, if if the cost is greater than 64 already, we should have no neighbors. So that can be like up here. We filter everything out and say if the cost is greater or equal to 64, then return none. We're going to walk no further than 64. Okay, so that should be it, I think. Let's print. Let's see if this thing is working. Reachable. Let's say, let's actually print something like this. We're gonna do reachable tiles, just collect a vector of this and see what we get for this sample. So cargo run, binary will be day 21, and the input is gonna be 21 sample. Woohoo! It's an iterator of Dijkstra reachable item, which has nodes and parent and total cost. Beautiful. Look at that. The first thing has cost 0. Is this the start? 5, 5. So S is at, yes, 5 over here, and 1, 2, 3, 4, yeah, 5 over here. So it also counts the starting position. That's good to know. So yeah, it is printing a lot of things. If we count how many of these there are, it's 81 total reachable things, but this is within 64, right? So for the sample, we should calculate just 6, which will be well, it's kind of ugly to hard code that, but let's just try it out for the sample until we get the correct answer. 29, but this is not the correct answer because we have to like filter out the 16 is what we want. We want to filter out the nodes that don't have the same parity, let's say. So how do we do that? Actually, we don't need to calculate the parity because these things, the reachable tiles, also have their cost, right? So it has a node, a parent node, and total cost. So we just need to filter out the things that are all the numbers here and only keep the even numbers because those are the ones that you can reach in 6 steps. But why are we? I wonder why we are reaching things that have higher costs. Because I printed this for everything. So now if we collect a vector now, we should see less stuff. We should only see up to things that are at that distance 6. So that's fine. That's fine. And if we do a filter here and filter the items that, let's say, item total cost is even. Don't numbers have an is? Look at that. They have is negative, is positive, but they don't have is even. That is a shame. So we'll do the usual parity check. So something is even if, the mod 2 is 0. Sure. And now if we run this, well, we get things that have even costs. Sure. And if we count these things, are they 16? Yes, they are 16. Awesome. So now let's do the same thing, but asking for 64 and passing in the actual inputs. And this is the number of tiles it counted. Let's see if this is the answer. And it is. All right, nice. That was a simple enough part 1. The code would need to be modified to handle the inputs if we want to print 16 for the sample input, but yeah, maybe I don't want to do that. I don't know. The elf seems confused by your answer until he realizes his mistake. He was reading from a list of his favorite numbers that are both perfect squares and perfect cubes, not his step counter. What? The actual number of steps he needs to get today is exactly this huge number. He also points out that the garden plots and rows are set up so that the map repeats infinitely in every direction. Oh. So if you were to look one additional map width or map height out from the edge of the example map above, you would find that it keeps repeating. So what was the map above? Yeah, it has this like empty exterior, and we see that it repeats, and we start from here. This is just a tiny 3x3 map slice of the inexplicably infinite farm layout. Garden plots and rocks repeat as far as you can see. The elf still starts on the same middle tile marked S, though. Every other repeated S is replaced with a normal garden plot. Whew. Here are the number of reachable garden plots in this new infinite version of the example map for different numbers of steps. For 6 steps, you can reach 16. For 10, you can reach 50. For 5,000, you can reach this number. However, the step count, the elf needs, is much larger. Starting from the garden plot marked S on your infinite map, how many garden plots could the elf reach in exactly this huge number of steps? Okay, so we have another part 2 that just increases, balloons out the numbers, basically. Beautiful, beautiful. And what did it say about this number? That this number was like perfect square and perfect cube. They're both perfect. Not hit step counter. 64 is a perfect square and a perfect cube. It is what is it? As a cube, it's 4 cubed, right? 4, yeah. 4 times 4 is 16, times 4 is 64. But it's also a square of 8 times 8. Okay. So this huge number, what about this number? Is this number a prime? No, it's not. It's 5 times 11 times this thing. Okay. But it's primey-ish, like it has a huge prime factor. So we need to move this amount, which is what exactly? 26 million. That's quite a lot. And it's even now, not odd. So sure. I'm tempted to, let's see if we have a chance of getting this, like brute forcing our part 1 solution. Surely it's not the intended thing, but let's maybe try. So the number of steps, we also need to do this infinite walking. So let's see if we can do 1,000 steps on the 16. Yeah, on the sample input. So 5,000. I just added this as a part 1 solution. Yeah, let's actually run check all. It's gonna fail on the input, but was this my number for? Yeah, this is the answer for part 1. So let's add that to our answers file. And for our sample input, we will need to say like 6, or just assume that 42. That's a nice number. Also, I wonder if it is an Easter egg. 42 would be the answer for part 1 for the sample thingy. So yeah, now all the checks pass. This is it's an okay thing for part 1. Let's have this thing extracted into a variable. Let's call this thing let's reachable tiles count. Yeah, and that's what we are going to print here. Okay, let's add this. Let's commit this thing. Add day 21 part 1 solution. And let's see how long, oh, left a comma there. Let's amend that. Sure. What would happen if we try to run this same thing for 5,000 steps, only 5,000, which is like way smaller than our actual number that we need to reach. But in 5,000 it already reaches 16 million, and this is like linear space, and this is growing like quadratically. So yeah, for 26 million, that thing squared is that's a lot. We won't be able to get part 2 by brute forcing, but I just want to have like an idea of this thing. Yeah, if it's more than 5,000, just cut out, and we expect this number, right? Yeah, 5,000 and 5,000 is even, so this check also should work. And if you run like this for the sample input, we will get also 42, because we are not looping around and considering an infinite map. So that's bad. Let's make this thing actually return a signed integer. So our positions are going to be signed integers. So in order to do that, let's use our zip trick here. And the problem with the zip trick is that it turns around these things that you are zipping, but that's fine. We don't do a wrapping add signed. We would simply add, right? Yeah, because now the things are signed. Sure. And then we try to get from the grid, but we have to loop around, basically. How do we do so? Well, the inputs are squared, right? 11 times 11, yes. And the input here is 131 and 131. And I think those are prime numbers too, right? Yeah, 11 and 131 are primes. I wonder if that's important, or is this just the advent of code creator, like being cheesy. But let's have then the size be the grid length. And what do I want to do? I want to get this will never be out of bounds. We need to do grid neighbor y mod the size, right? And let's treat size as signed integer. And if we and an x mod size as isize. And of course, once we do the mod, we need to then convert back to unsigned, which should be okay to do. Beautiful. Then we have the wrapping tile. We do the wall detection. That is still correct. And okay, let's see what this prints for the sample, and if it even is able to run. Well, we did get a out of bounds. The index was this huge thing. Okay. Okay. This index was out of bounds, I guess. So what happens if we underflow here? Like n. do we get a negative number? Like, how does mod work in Rust? Oh, I think I remember. Do I remember? Yeah, if we print, I want to see basically this thing is being negative at some point. So if is less than 0, let's print ln negative ny, and just print this thing. And let's also print our ny and like the mod thing results of doing this. Sure, before we panic. Okay, maybe it's panicking in the other axis, in the nx axis. So let's actually print if nx is the negative thing. Yes, negative nx, just -1, sure. We do the mod with the size, but mod is not doing what we want. I think what we want is called something else. Should be called rem Euclides. And there is one, there are some other rem operations, one from pathfinding num traits. This non-negative reminder of okay. Here it says basic usage, but there is no a function here. Okay, but that's not what num trace Euclid. Yeah, probably that's not what I want. There is a rem Euclid on the standard library. So am I using that? I think so. Yeah, okay. Let's do this with a size, shall we? And size, I guess, will need to be, yeah, as size. Does this work now? Yeah, now it -1 wraps around. So that's what we need to use, I guess, for nx, and it will return the same type. So we still need to do as you say. Yeah, we still need to do that. That's fine. Let's do the same with ny. Beautiful, beautiful. And clean this up. And if we run now with a sample, it's taking its sweet time. And this was just 5,000 cost, and you should find 16 million something. Yeah, 16 million. So we have no chance. And let's run with in release mode. My computer is moving because once again my cat is sleeping underneath. So okay, this is not getting our answers. Let's dial it back to 500, shall we? This is very slow. Maybe I made a mistake and this is never ending, so let's check with a much smaller. Okay, for 500 is this number, which is correct. So the logic of this is looping around correctly. Beautiful. But increasing to 5,000, it is, well, this was 160,000, and increasing, yeah, you can see like increasing this 1 0, like increasing by 10 is increasing the result, increasing the input 10-fold is increasing the result like 100-fold. So it's quadratic, of course. So if we want to go from this up to this number, which is 26 million, it's an increase of 5,000 to this is like 5,000 times more, if I'm not mistaken, more or less. So, but it should, like, the output will be 5,000 squared more. So it's, yeah, it's unimaginably larger, and it's just going to take way more, like way too much time. And you can see that also probably that like this Dijkstra algorithm is not scaling very nicely to this, which is also a pity. So yeah, our part one solution does not scale up to part two. I want to maybe kill this thing, and let's do a cargo build in release mode, and then I'm going to run this with the same sample input, but run the targets, release day 21, and time this thing. So yeah, while that is running, can we think about something? So I can think of a couple of things, actually. The most obvious one is that if we walk this ginormous number of steps, most of the maps, like most of the, let's say, how do you call this thing? Like garden tiles, but you know, I don't mean each dot, but this like super tile that we are repeating will be covered fully. Like everything that is less than this size, like some of them are going to be cut diagonally, but a lot of them will be covered fully, and they will have like, they will contribute the same amount of steps. Although we saw that this is 11 and in size, and the other one was 131, which were prime, sure, but they are also even, because yeah, most primes are, no, sorry, not even odd numbers. Most primes are odd numbers, of course. The vast majority of them, I think, mathematicians would say. And that means that like the parity, our parity thing we do here would change between, like we have another parity check, because whatever, like imagine that this tile, like the 0, 0 here, is reachable. Well, when we repeat this thing over here, like we can probably do that if we do some multi-cursor editing. When we repeat this over here, this would be what corresponds to 0, 0 here, but now this tile is the 12, so 11, oh, 11, 12, so it's also, it's also even again, I was not expecting that. My parity brain is messing up now. Why is this the case? Like this is the, if this was 10 by 10, we would say like this is the first one. I think I'm getting screwed by zero indexed thinking. So this is index 10 in our okay. Yeah, I was seeing the columns, but columns here are 1 based index, and I'm thinking of 0 based index. So doesn't matter. Let's be consistent. If we consider this 0, 0, this one on the repeated thing would be 11, 0. So it changes from even to odd, and it will alternate. And that is the case for the sample because it's an odd size, and it's also the case for the input, which is also an odd size. And it's the same thing if you do 1 base index, of course, because this would be the index 1, 1, and here it would change to 12, 1, and so 12 is it changes like from odd to even. So you have to take that into account, but I guess calculating like a full map contribution, like the even and the odds, would be enough. But then you would have to know how much you can walk. How do you do that? How do you have any idea? Of how long you can walk. This should have finished, right? Okay, yeah, it finished in 28 seconds. So how did we say that we have to increase this? Like the actual inputs we have to put, this was 5,000. We have to try out 25 million something or around that, which is 5,000 times more than this. So the actual output will increase by that number squared, so 5,000 squared. So if this took 100 seconds, the runtime that it would take to use our actual number would be 25 million times 100. It's a lot. Like is it like 2.5 trillion seconds? I'm not sure, but something around that, I think, or not. 25 million? No, it's 2.5 billion seconds, so it's not that high, I think. But still, it's way longer than I can wait. Yes, I don't know if I would live that long. I don't know. Calculating number of seconds in lifetime is not something I've ever done. So that's definitely not going to scale. And of course, before that, it will probably run out of memory too, because all this Dijkstra algorithm needs to like keep track of what you have visited. So that will also balloon out and explode and not fit in memory and crash. So yeah, sad. How could we do this? So one thing that I'm thinking about is you will sort of reach all of this. Okay, this input is interesting that it has like empty outer walls. The sample, I mean, I don't know if the input also complies with that. It seems so, right? Yeah, it seems like the outer layer doesn't have any walls. That is sort of interesting. Like besides the big rhombus here, and the start is at the middle. Like the start is also at the middle. That's also interesting. Like both of them were odd sizes, and yeah, this is starting at 60 column 66. So it is exactly half of the middle point of 131. Great. That I think is also important. We also, oh, look at this, look at this. We also have an uninterrupted line of sight to the left and to the right of the starting plot. And is that also true going up? Let's see. We go up and up and up and up, and we select all of this. These are all dots. Okay. If we go down, these are also all dots again. All right, that is our clue, I think. That is our clue. So, whenever we get to these like repeating things, remember we are walking in this north, south, east, west directions. So since we can have a direct line of sight to here or to like in every direction to reach like the next repetition of this, and also we have clear borders, so we can also move freely on the borders. So we can actually like count the distance, precise distance to any border, like the distance to, you know, even considering walls, because we can avoid walls, because we can walk directly in there. So that's interesting. That has to do with this particular input shape, but it's nice. So I'm also wondering if this exact number that we are given is like special. Let's do this thing. If we do this thing divided by 131 float, well, we do have a reminder. If we do this mod 65 is a good reminder because that's exactly the middle point of where we start. This is our starting coordinates, 65 and 65. Okay. This means, I think, that we cover entirely all of this like super tiles. I think, I'm not exactly sure, but I think so. Right? Okay, so if we think that that is true, let's suppose that this is true. I was thinking that I was not going to try part 2, and I would cut this video, but now I have this hunch. So we know that it will take 65 to get to the border, and then we repeat. But we sort of know, like, what does this tell us? To me, this tells us that we are going to be able to access, basically, let's do this minus 65. Not exactly sure, but no. Division, and this should be an exact division, right? Yes. And we divide it by this size. This might be like the distance we can go up or down, or a combination of those, for accessing, like we would access any maps that are this distance away. And by the way, since we are starting on the middle of this, how does parity affect these things? I think the parity still like switches. That will still be true. So I think we probably need to take that into account. But okay, let's try to minimize numbers, right? Let's try to think about a much simpler case. A much simpler case. So let's write actually a new sample. This sample, well, let's think in this sample file, because I don't care about this. Let's say that we start here and it's a 3x3 thing. So much simpler than what we actually have. Okay, so this is our whole input. No walls, so because we don't care about walls. Let's not care about walls. And we are asked, okay, how much can you go? But this time it's the total distance would be 4, right? So if the total distance is 4, this thing would be repeated. How do we write this? Let's copy this thing. This is sort of like the repetition, although the starting things are not exactly like this, but yeah, okay, kind of like this. This would be the starting point. Let's consider these other things, like, I don't know, walls. They don't matter. They really, or they actually, no, they actually do matter because we need to see a clear line of sight. Sure, let's say they are all this. They are the real starting point is here. So if we consider like what we can reach in 4, what we'll have, okay, yeah, the actual, I think we need to still consider like the different pointy bits of these rhombuses. Yeah, so the last one is like you will encounter the last, like the rightmost supertile that you will encounter. You will have 3 left to walk, distance to walk, and you can start here basically. How much you can start from here? Because starting from here would be, oh well, from here or from here, because those are tiles from this, is kind of the same, because the minimum distance is still going to be like walking like this and in a square manner. They won't be less distance than that, right? And that will be the rightmost. Then the leftmost you can do the same, like starting from this side. The topmost you can do the same, like starting from the bottom side, in the middle, and the bottommost you can do that. And then you will have all the diagonals that you have to also consider, like starting from one of the corners and filling up for exactly the size of the map. Basically, that's how long you can walk. And then I think it would be a matter of like doing some multiplications of those. Like you will have one of each corner plus a lot of the diagonals plus a whole bunch of field maps. So I think that's kind of the idea that we can do. I need to go to the bathroom for the amount of mate that I have been drinking, and I want to take a break from this. I will try to think a bit more of this in the abstract, but I think that sounds like a promising approach. Like, okay, not consider this thing looping around like how we did with this sample and 5000, but like take into account that the number that we want to move, if we displace by the starting position, is exactly like a multiple of our map size. Yeah, and then like most of the maps that we are going to move around are going to be just repetitions of each other, so we can just compute them once and be done with that. Yeah, and I think that will be it. We have to like carefully compute the number of reachable things starting from different points of the map, and then do some careful multiplication of those, which we can think of like starting from small numbers and, you know, finding the pattern going up. So yeah, I think that will be the plan, but that will be for the next video. For now, if you have been, thanks for watching and see you later. Bye bye.